Recently, I've seen a lot of videos on exponential equations. And when you start looking into details, you find that really there are 2, 3 ideas behind how to solve these equations, and that's it. So I thought, why do we need hundreds of videos on the same topic? We can just have one where we discuss all those techniques. And really, if you understand these techniques, know how to use them, you will be able to solve probably 90 or even more percent of all the exponential equations that you can experience, you can see in high school. So let's get started. First of all, we're going to look at a very simple equation, 2 to the x equals to 8. To solve this equation, we just need to realize that 8 is 2 to the power of 3. Now if we look x here, 3 here, we've realized that x equals to 3 is solution of this equation, and we are done. Another equation, a little bit more complicated, but really not that much. If we know what logarithms are, we just take a logarithm base 2 from both sides of this equation, and we get the final answer is x equals to log of 3. Now, I solve this equation not just because I wanted to solve this equation and show you how to solve this equation, because these equations are very simple, and I presume everyone knows how to do that. I brought these examples because sometimes when you watch these videos of people solve this, they leave something behind, something very important. And the important part here is the fact that once we find one solution of these equations, that's it. We found them all. But if you think about it, we are solving nonlinear equation. And nonlinear equations very often have more than one solution. So what guarantees us that once we find one solution, we don't need to look for any more? And the answer is monotonicity. Monotonicity of the exponential function. So if I have exponential function like this, a to the power of x, if a is greater than 1, I'm going to have a monotonically increasing function, or more precisely, strictly monotonically increasing function. And that means that when x goes up, a to the x also goes up. When a is between 0 and 1, we have monotonically decreasing function, more precisely, strictly monotonically decreasing function. So when x goes up, a to the x goes down. And it turned out no matter whether we have monotonically increasing or monotonically decreasing function, as long as we have one of those two monotonicities, and we're trying to solve equation like this, f of x equals to c, where f of x is monotonic function. It could be monotonically increasing or monotonically decreasing. We are guaranteed that this equation has no more than one solution. So how do we know that? Well, let's consider a case when f is monotonically increasing function. The same proof can be applied when f is monotonically decreasing function. So let's have this function monotonically increasing, and let's assume that this equation is satisfied when x equals to x star. At that point, f of x star equals to c. And now you can see that for x less than x star, because this function is monotonically increasing, f of x should be less than f of x star, which is c. For x greater than x star, f of x should be greater than f of x star, which is equals to c. And therefore we see that f of x equals to c only at one point, and that's when x equal to x star. Now one comment here, that what we show now is if we have one solution, that's the only solution we're going to have, provided that f is monotonic function. Now, in general, there's also a possibility when this equation doesn't have any solutions. So, for example, equation like this, 5 to the x power equals to minus 1. If you consider real values of x, and those are the only values we're going to consider here, 5 to the x power is always greater than 0. So obviously it can never be minus 1. Okay, so now we consider this case when we have monotonic function equals to some constant, and we said we can have either 0 or 1 solutions. The other situation that sometimes people see is equation of this type. We have some function f of x on the left equals to some other function g of x on the right, and we know that one of them is monotonically increasing and the other is monotonically decreasing. And in this case, we have the same story. So this equation can have no more than one solution, either 1 or 0. How can we prove this? Well, the proof is very easy. If you look at this equation right here, let's subtract g of x from both parts of this equation. We get an equation like this. Let's modify it a little bit. And this is what we're going to have. Now notice what we have on the right is 0, constant. What we have on the left is the sum of two functions. First function is monotonically increasing function. Now the second function is actually monotonically increasing as well. So g of x, we said, is monotonically decreasing. And when you take minus g of x, you get the opposite, monotonically increasing function. If you take monotonically increasing function and add to another monotonically increasing function, you get a monotonically increasing function. So here we have really this situation when on the left we have a monotonic function, on the right we have 0, a constant, and as previously shown in this case, this equation can have no more than one solution. All right, how can we use all this information? So let's start with an equation like this. 9 to the power of 3x minus 1 equals to 3 to the power of 2x plus 3. First of all, let's use a property of exponential functions, that a to the power of b plus c equals to a to the power of b times a to the power of c. If we apply this property, we're going to get something like this. Next thing to notice that 9 to the power of minus 1 is 1 over 9. Here we use the property that a to the power of minus b equals to 1 over a to the power of b. And the next thing we're going to do is to notice that 9 is actually 3 squared. So in this case, 9 to the power of 3x could be written as 3 to the power of 6x. And to get there, we need to use a third property of exponential functions, is a to the power of b to the power of c equals to a to the power of b times c. Now we're going to substitute this value instead of 9 to the 3x right here. That's what we're going to get. And the next thing we're going to do, we're going to multiply both parts by 9. The next step is to divide both parts by 3 to the power of 2x. And that's what we're going to get. Now here I also use the fact that 9 is 3 squared. The next thing, we're going to use this formula again. So to notice that 1 over 3 to the power of 2x is 3 to the power of minus 2x. And also notice here we have 3 to the power of 3 times 3 to the power of 2. According to the formula right here, it's 3 to the power of 3 plus 2. In a similar way, we can combine the left-hand side, and we get 3 to the power of 6x minus 2x. And that gives us the equation like this. And this equation is very similar to what we had before right here. You have 3 to the power of 4x equals 3 to the power of 5. It means that 4x should be equal to 5. And as we discussed before, because of monotonicity of this function on the left, this is the only solution we can have. And that means that x equals to 5/4 is the only solution of this equation. All right. Let's look at another example. Here we're also going to do some manipulation with powers, but also there is another idea that we're going to see in a second. So first of all, notice that we have 4, which is 2 squared. So 4x will be equal to 2x squared. Here again we use this formula a couple times. We substitute this instead of 4x right here. Now notice that if we create a new variable t equals 2 to the x, we find that we have a quadratic equation here, t squared minus 5t minus 6 equals to 0, which we can easily solve. Just to remind you, if I have a quadratic equation like this, it has 2 solutions, which represent these formulas. If you work with this equation, you'll find there are 2 solutions. One is t equals to minus 1, another t equals to 6. Now remember, t is 2 to the x power, so t has to be positive. It means that minus 1 is not really a solution of our equation. So what we really need to use is 6. So 2 to the x equals to 6. We know how to do it. We've done it before. Apply log base 2 to both sides of this equation, and we get this x. That's the only solution of this equation. Here's another equation that basically is solved in a similar way as the one we had here. So we're going to do some manipulation with these exponential functions, and then we're also going to do substitution, and that substitution will make this equation as some algebraic equation that we can solve. So in general, that's one of the ways we can solve equations, when substitution gives us either a polynomial equation or some rational equation or some other equation that we can solve. So here, to solve this problem, we need to realize that 49 is 7 squared. And in this case, 49 to the power of x is 7x squared. 36 is 6 squared. In a similar way, 36x equals 6x squared. And 42 is 6 times 7. So 42x will be 7x times 6x. Now we're going to substitute all of these things in our equation. And we're going to divide left and right hand side here by 6 to the power of x squared. If we do, this is what we're going to get. Now remember that 7 to the x power divided by 6 to the x power is simply 7/6 to the x power. If we do that, we already see that we got a quadratic equation with respect to 7/6x. So if we introduce new variable t as 7/6x squared, we're going to get polynomial equation. In this case, it's quadratic equation, easy to solve. And if you solve this equation, we find 2 solutions right here. Both solutions actually are positive. So really it means that there are 2 solutions to our original equation. So 7/6x could be 2 plus square root of 3 or 2 minus square root of 3. We'll take log base 7/6, apply to this equation, and we get our final answer, or find our 2 answers, one with plus sign and one with a minus sign. Now let's consider this case. And it turned out that this is a different type of problem. In this case, no matter how much we try, if we try to play with exponential functions, if you try to find some kind of substitution to create algebraic equation we can solve, nothing of this kind works. So the solution in this case to this problem, the strategy, is to guess a solution. And we can quickly see that x equals to 2 is a solution of this equation. Because 3 squared plus 4 squared equals to 5 squared. That's actually a Pythagorean theorem applied to the Egyptian triangle with the sides of 3, 4, and 5. Now, the next thing is to actually using some monotonicity properties to show that there's no other solutions in this equation. And in this case, we will be done. Now, if you look at the equation written this way, well, we can't really do it right away, because 3 to the x, 4 to the x, and 5 to the x are all monotonically increasing functions. Now what you have on the left is the sum of two monotonically increasing functions. That's going to be also monotonically increasing function. But on the right, we also have monotonically increasing functions. So monotonically increasing function equals to another monotonically increasing function. That doesn't tell us anything. There could be as many solutions as you want. You can always come up with an example. If, let's say, left-hand side was monotonically increasing and the right-hand side was monotonically decreasing, that would be a different story. But that's not our case. So we need to manipulate this equation. And manipulation is to divide both parts of this equation by the right-hand side, by 5x. If you do, this is what you're going to get. But now notice you have 3/5 to the power of x. 3/5 is less than 1. So this is monotonically decreasing function. 4/5, for the same reason, is also monotonically decreasing function. Now we have one monotonically decreasing function and another monotonically decreasing function. When we add them together, we're also going to get monotonically decreasing function. And now we get what we wanted. On the left, we have a monotonic function. On the right, we have a constant. This solution can have either 0 or 1 solution. We already know 1 solution, so that's it. We cannot have any more. Problem is done. And now look at the last example. And it turned out that this example cannot be solved by any of the techniques we discussed before. Now, what we can do again, we're going to try to guess the solution. And when we start guessing, we quickly realize there are actually two solutions, at least two solutions to this equation. X equals to 2 and x equals to 4. Now, obviously, when you have two solutions, now we can't really have some kind of monotonic argument, because that would only give us one solution. So we have to do something else. And in this case, we really need to investigate the left-hand side, how it behaves, where it goes up, where it goes down. So we're going to look at this function and see how it behaves. And to do that, we want to use tools of calculus. So what do we want to do? We want to calculate derivative of this function f, which is equals to this. To get this formula, we just need to remember that derivative of a to the x is a to the x times natural log of a. And what we want to know that where this function is positive, because that would indicate that f function goes up, and where this derivative is negative, that would indicate the region where our function f goes down. So to do that, first let's find the points where the derivative is 0. To do that, we need to solve this equation. It's an exponential equation, actually, with respect to x star. What we can do, we can take the second term and move it to the right-hand side. Then we're going to divide both parts by 2 to the power of x star and by logarithm 3. If we do, that's what we're going to get. Now here as before, we take log based square root of 3 over 2 from both sides of this equation, and this is what we're going to get. So really what we find that derivative equals to 0 only in one point. And since there's only one point where this derivative equals to 0, it's actually sufficient to say that the original function f can take this value 1 in no more than 2 points. Okay? But now let's go step by step and see how I can come up with this conclusion. First of all, if this derivative equals to 0 at some point, there are 4 possibilities for the derivative. First possibility is that for x less than x star, the derivative is positive, but to the right of x star, derivative is negative. Positive derivative means the function itself goes up. Negative derivative means the function goes down. The second scenario is the opposite. So on the left, derivative is negative. function is decreasing. On the right, derivative is positive, function is increasing. The third scenario is when the function is actually positive to the left and to the right of this point x star. In this case, in both of these intervals, the function is increasing. And the last case is when derivative is negative, both left and right. In this case, function is decreasing in both intervals. Now, we know that these two cases cannot happen. And that's because that would indicate that our function f is monotonic. A monotonic function, when we're looking for an equation where monotonic function equal to a constant, can have only one solution, 0, 1. But we already have two, so that doesn't work. So we have one of those two cases. But regardless of what case you have, if you look for x is less than x star, in both cases we have monotonic function. So in that range, you can have up to one solution. If you look to the right of x star, again we have monotonic function in both cases. So to the right we can have two solutions at most. And therefore, one solution on the left at most, one solution on the right at most, total maximum two solutions. And that's what we have. Now, if you're really interested which way the function goes like this, it has a maximum, goes like this, has a minimum, we can actually quickly check it. Just pick up a couple of points. Let's say we take x equals to 0. If you do, you find the derivative is positive in this case. And if you pick up another point, let's say x equals to 4, we find the derivative at point 4 is actually negative. So we have the case of maximum. And this is it. So today we consider multiple equations. We solve equations with using different techniques. So if you can master all these techniques, you're pretty much going to be set for 90+ cases of exponential equations you see in high school.